Today, I want to look at one of the most basic topic in radiology, X-ray production, because most of the facilities, most of the equipment we use in radiology are actually X-ray emitting devices. So it would be a good way to start by looking at the basics of X-ray production. Talk about CT, talk about conventional radiography, mammography, fluoroscopy. They all make use of the principle of X-ray production. And an understanding of the basics of this will actually help us appreciate this equipment the more. And of course, also know why we actually need to take care of this equipment, because the tube, which is the insert, which is the portion that creates these X-rays, are actually very, very important, very, very delicate, so to say. So we need to know these basics. So today I want to look at X-ray production. X-rays, like we know, is part of the electromagnetic spectrum, one of the portions of the electromagnetic spectrum. It comes before the gamma ray. So it is highly energetic. And right from our secondary school days, we know that we can divide them. We have basically two types of X-ray: soft X-rays and the hard X-rays. Soft X-rays are those that have minimal energy, while hard X-rays are the ones that have higher energy, that can penetrate matter to a great extent, and can form image when we so desire. When we have an image receptor at the other end, we can actually use it to form image. So I want to look at X-ray production. Before now, we have seen, or we know an extent what Bremston is. Bremston, and then we also talked about characteristic X-rays. These two basically form the X-rays we use in X-ray radiography. I want to first of all look at the Bremston, which is the major component of X-ray. It has say more than 95 or even 98% of an X-ray spectrum that we use in X-ray, while a characteristic is just a little amount. Of course, when we come to mammography, we see that we make sure we try to increase the portion of the characteristic X-ray. So look at Bremston law. So the production of X-ray, I say it is based on both Bremston, this is the double S, and then characteristic. Let me just say X-ray Bremston X-rays. So, but before then, X-rays usually produced in an X-ray tube, which composed of the X-ray method, the enclosure itself, which is the X-ray tube, which has the cathode and the anode. The cathode is the negative. Okay, let me quickly share something to make it. To actually capture the moment very well. Oh, we can see the screen. Can we see the screen?
Yes.
Okay.
Yes, sir, we can see.
Okay. Thank you very much.
Yes, sir.
So this is basically the most important so this is the most important aspect of X-ray production. The X-ray tube, the most important piece of equipment we have there. We have the X-ray, the evacuated glass tube. It could be glass tube, it could be metal tube, depending on the choice of the manufacturer. Of course, if it is going to be a glass tube, it has to be a very, very strong one. Of course, it is evacuated. The envelope here is evacuated. By the envelope, we mean this casing is evacuated. That is, we it's almost a vacuum. It is as much as possible. All the air particles, everything there has been removed, especially air, so that it doesn't affect the movement of the electron as they are produced from the cathode. This is actually a cathode, which is the filament. Okay, it has a filament. The filament is heated up. And most times, the filament is usually tungsten, because tungsten can actually, tungsten is element M74. M74, it can withstand very, very high temperature. So it produces electron by the process of thermionic emission. By thermionic, we mean heat. So when heat is supplied to this, and where does the heat come? The heat comes um, from the circuit of this cathode, from this filament. It has its own circuit. The circuit produces electric current, and the electric current is the one that, of course, and just like normal heaters at home, when you heat these things up by plugging into the mains, electric mains, but something becomes heated up. In that process, electrons are emitted, so we don't see them. Electrons are emitted, and then the electrons emitted will not travel straight down to to the anode. The anode is, of course, is the target material. And again, most especially, it's also made up of tungsten because of the earlier properties we mentioned here. It has a high absorption rate. It can withstand heat and so many other things. And then we have the copper anode. This copper is also part of the material, part of the anode material. Its function here is to conduct heat away from this tungsten. And we have now before then we need to know some of the little principles involved in the movement of electron from here to this place. When we apply a voltage between this cathode and the anode, or if you don't apply any voltage and we just begin to apply our electricity between these two ends, between this, of course, this is the cathode, but even before then, we have negative and the positive terminal here. If I apply electricity between these, this thing begins to heat up. This cathode begins to heat up. We now have a concentration of electrons here. The electrons wouldn't go anywhere because there is no potential applied between the cathode and the anode. But immediately we begin to apply potential, we apply a potential difference between this cathode and then this anode. Then something begins to happen. Electrons begin to drift from the cathode to the anode. And the rates, the kinetic energy with which they drift depends on the voltage applied between them. The voltage applied between them is 100 volts. They will have an energy of 100 electron volts. If the voltage applied between them is 200 volts, the electrons will have a kinetic energy of 200 electron volts. So the energy depends on the application of the difference in the voltage applied between this anode and this cathode. So the electrons, when they impinge on this material, they are decelerated. The electrons are decelerated. And the loss in kinetic energy of the electron will now result in the production of reduced X-ray, of course, by the principle of mass energy. Mass is now converted to energy. So energy is conserved, and in the process of conservation of energy, X-rays are produced. So these X-rays, they are produced isotropically in all directions. We have them this way, that way, all the directions. But for our purpose, we want to have an outlet around this area. So that was why this has been drawn for just purpose of elucidation. As is, we have, this is just a schematic diagram of what happens. This is just the only the tube one there. But inside this, with this tube, we have an insert. And inside the insert, you have so many other things. We have a window, we have a mirror, which defines the X-ray beam, and then so many other things. So we now have an outlet here. The outlet here is made up of lead strips, X and Y plane. We have four jaws, four collimators. They are usually made up of course, lead, just to define the field that, just to define the place we want the X-rays to exit. And also, and this the whole of this is also enclosed in a lead shield. Everything is enclosed in a lead shield, so that all the other electrons emitted in every other area which are not needed will be absorbed by the lead shield, leaving only the ones, the openings we have provided as the outlet for the useful X-ray beam. So this process gives us is what actually the Brent is. And then it is also what it is known that most of the energy given off, most of the energy of the electron, or most of the energy of these electrons coming up are lost as heat. The energies are usually lost, most of them are lost as heat, collisional energy um, within the material, so on and so forth. Whereas just a very, very little percentage, in fact, about 1% of the energy supplied to this cathode or supplied by this cathode eventually ends up as this wax will be. So that is why we need this copper here. And of course, we also have some oil bath, which helps to reduce the heat accumulated here. So it helps us to evacuate the heat produced. And that is why the X-rays are not turned on for a very, very long time. Because if that happens, of course, it can actually lead to tube failure. In fact, modern X-ray tubes these days, they have some um, kind of circuits that wouldn't permit you to expose more than particular um, temperature range. I mean, more than a particular time. For example, if you want to do a particular operation and then you press the button, the exposure button for so long, it doesn't matter the amount of time you have pressed it. Once it gets to the saturation point, the needed exposure and parameters, something will just short. I mean, stop exposing. So this is just a little the schematic diagram of X-ray tube. This is what we see in all X-ray emitting material, both cathode and perovskite. This is the basic of all of them. Also, we continue, and so the Bremsstrahlung long as the electrons come. And the electrons come over and then hit the 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 cathode, I mean the anode. We have conduction. So this is the process. This is a cathode. I mean, this is our nucleus. As electrons come over, electrons come. Some electrons will actually approach, will be very distant from this. And of course, this is a positive, these electrons are negative, they'll be attracted to it. To form a kind of deceleration. So we come here, very close to it, I mean some distance away from it, they will also be accelerated. Whereas some will come into the proximity of the nucleus. This one will undergo the greatest amount of retardation. So these ones, we have the greatest amount of retardation, which implies that they have the rate at which the electron's energy change is maximal here, followed by here, whereas this one is the minimum. The minimum. So the difference in energy of this electron here and the difference in energy of the incoming electron will now give rise to an X-ray whose energy is the energy difference between this and two. This one will have a low energy, this one medium energy, whereas the one that impacts with the nucleus will give off all the energy to the nucleus. And this one happens just a very, very limited amount of time during interaction. You can have it, it's usually less than 0.5% or so because of the nature of the nucleus. The nucleus is just a very, very small portion of the whole atom. So the probability of electrons impinging on this nucleus is very, very small. So, but when that doesn't happen, it's just a very, very small amount of electrons that will impinge, that will hit the nucleus, giving rise to the maximal amount of energy. For example, if the energy between the cathode and the anode is 200 electron volt, it is only the electrons that come across this nucleus that will have an energy of about 100 and 200 electron volts. If we have, if we apply the voltage between the cathode and the anode to 200, it's only the electrons that come close or come in proximity, or mean come directly in contact with this nucleus that we have 200 electron volts. So these ones are usually, so that is why if you look at the spectrum of what's it called, the Bremsstrahlung. The Bremsstrahlung spectrum goes this way. Sometimes it might be required, like in the last Viva West Africa times, some of you were required to draw on this diagram. So the spectrum for the Bremsstrahlung is actually this way. Assuming we are operating at an energy of 200 volts, the maximal energy of the X-ray will be 200 electron volts. And you can see this is the number of X-rays. This is the energy. You can see the ones that have a very low energy, they are more. As the energy decreases, as the energy increases, the ones that have this high energy are very, very minimal. But as the energy reduces, the number increases. You look at the probability. So the probability of the ones that have lower energy are more than the ones that have high energy. So that is why it is needed, usually needed, to bring in some filters to remove this very, very low energy. Because this very, very low energy will actually constitute, wouldn't constitute any a good image. It won't constitute good image. They will only end up causing, what's it called, exposure on the patient. It wouldn't be useful for image analysis, for image quality. So in that case, if you now filter, it is unfiltered and spectrum. This is unfiltered and spectrum. If we filter it, that is, we add a filter to the stuff, to the X-ray tube, you have something of this nature. Assuming you have a filter that removes energy from 0, from 1 or whatever to 20. Let's say this is a 20 electron volt. Now have the spectrum becomes this way. So spectrum will now be this way. So this is our filtered, is the filtered spectrum. The filtered and spectrum. So this is all there is, because at this level, this is all we need to know about the Bremsstrahlung long X-ray. Then characteristic X-ray embedded on this on this, okay, or this way, since the electrons do not only interact with the nucleus or the surrounding of the nucleus. Some electrons also interact with fellow electrons on the electronic chairs. Those ones constitute what we know as a collisional energy losses. And of course, we have done all those ones before. So those ones constitute collisional energy losses, which is dependent on the binding energy of the electrons in all the shells. So the electrons so this is our K shell. Of course, this is the most important shell during X-ray production, because all other ones are not so useful. All other ones are not so useful because of their distance of propagation. Because when electrons, when you detach electrons from this K shell, electrons from other subsequent adjacent shell will come down and then take the place of the ones that have been ejected. So the major concern is the K shell, because if you have electrons, of course, some electrons will be detached from this, but the energy is so small, because the ones here will come up to fill this energy gap here, this vacancy here. And the difference between the force and this is like KF. Difference between L and M is not so wide. So this one, the characteristic energy or the characteristic energy that we given out here is very, very small. So it is only the transition of only the interaction of the electron with the K shell that actually gives very, very useful characteristic X-ray. So the K shell is the one that's it. So when this one happens, of course it does happen. We are going to have a modification to this. We now have some spikes on this, we now have some spikes on this filtered and spectrum, depending on, you can have KH spike, alpha 1, alpha 2, and so on and so forth. So this is the characteristic portion of the X-ray of the X-ray that has been imposed on our Bremsstrahlung, on our filtered Bremsstrahlung spectrum. And of course, this one, they have their particular energy. Their energies are constant, because the binding energy of each shell has a constant value. So that's just the brief about the calculation of X-ray based on the Bremsstrahlung and the characteristic energy contribution. Before I continue, do you have any questions?
Yes, good morning, sir.
Okay.
Uh, yes, sir. Please, can you please go over the graph, that sketch you made before explaining characteristics?
Okay.
Please, can you please go over it again? Thank you, sir. Yes, sir.
So this is a graph of this the number of X-ray photon. This is the energy. At times we might be asked an intelligent question during Fiverr. Um, you might be asked to actually draw a representative graph of an X-ray tube operated at 140 kV. If you have an electron operated at this, when we set these parameters on the radiographer just set the parameters. Wow. Just put these values. The values, the tube, we now press the tube. We have something just warms up to this, warms up based on the parameters we have provided. Then specifically on this 140 kV, it means the energy of the electrons. The energy of the electrons, the kinetic energy of the electrons, we have will be 140 keV, because energy is just a potential multiplied by the electric field. Okay. So we have the energy of the electron about 140 keV. So that's the maximum energy before the X-rays we have. No X-ray will have an energy greater than 140 keV, because the electrons will strike the target at different levels, at different depths, which is because of the nature of the atom. So it's like some come here, and this that way. Electrons will come here and then lose almost all the energy. The ones that lose almost all the 140 keV will now give rise to X-rays of 140 keV. Whereas this one will give rise to lesser amount. But the probability of the electron coming in contact with the nucleus is very, very small. So that is why you have very, very small amount here. So 140 keV will be here. 140, these are 140 keV will be here. But this one now goes up. This one has probability is very, very small, having this energy. But the ones that have very low energies are very, very high, because we have so many of them. And see the probability, so many of them, so many. So many will come this way and that way, so on and so forth. And as the electrons are being deflected, they are undergoing so many other forms of a reaction, a photoelectric effect comes in, and so on and so forth.
Yes, yes, sir. Please, before you go further, are you then saying that the higher the energy, the higher the number of X-ray that will be produced?
The higher
is that the correlation?
No. The higher the energy.
Okay.
This is the energy spectrum. We have a lesser number of X-rays at this energy, at higher energy. At the energy.
Okay.
This is higher.
Okay.
At higher energy, we have a lesser number.
Yeah, almost zero X-ray.
Yeah, almost zero.
Okay.
At this.
I get now, sir.
Okay.
Yes. I guess now. All right, sir. Thank you very much, sir.
So we have okay, 5
Hello,
minutes.
sir.
Okay.
Good morning, sir.
Yeah, good
This is
morning.
Dr. Clarissa. I don't know whether I can say something about the best shalom, sir.
Okay.
Can I go ahead, sir?
Yeah, you can.
Okay, sir. I just want to add that in filtered best shalom, the
In
maximum production filtered best shalom,
okay.
as in the filtered one, we have the maximum X-ray production around 1/3 to 1/2 of the maximum energy across the tube. That's
Yes.
what I wanted to add, sir.
Yeah, that's correct.
Thank you, sir.
That is correct. So we have so the X-ray tube. So let's just look at some of the components of the X-ray tube. Of course, major components are cathode, the anode, the oil tank, the rotor, the starter, or the exit window, exit window. Okay, see around 4 minutes. We have the glass or metal envelope. And let me quickly show us the tube housing, and then what's it? And of course, there's so many cables. I think we can 3 minutes. In 3 minutes, we should be able to do all this. So let's quickly look at some of this part of the X-ray tube. We have this one is basically for a rotating anode. Of course, we have two configurations of the anode. We have the fixed anode and the rotating anode. The fixed anode is usually made use of in equipment that don't require so much tube loading. That is equipment that we don't so much use, like we have in some mobile X-rays, in some portable fluoroscopy machine, like some C-arm fluoroscopy, and yeah, basically. But most others use a rotating anode, and rotating anode is so used because the tungsten, the anode that rotates, and as it rotates, it dissipates some heat much more effectively than if it were stationary. So the ones stationary can make do with the heats, the heat generated, because you just use them sparingly. But if you need volume, if it's in a facility that uses sees so many patients, of course, it's no longer feasible using the fixed anode, because of course the machine will always the tube will always fail after some use. So you have the rotor, which is the rotating part of it. You have the starter, which is connected close to the rotor, that energizes the rotor to begin to rotate. Then these are cathode, of course, and this is a filament and cup, which most times you have a two fixed on stay this same stuff, this same focusing cup. We have them two. We have one that has two, small focus spot and a big focus spot, all in the same. Most X-rays have that. want to make the image a very big and patient, I want to use a smaller, I mean, like the bigger focusing, just press the big focus scope. And if it's a bigger, of course, it is advisable to use a smaller and focusing and top. And these are tungsten, blah, blah, blah. So these are actually, then this is the glass envelope. These are actually the parts of the X-ray tube. I think I have to continue in a short while. Just in a few seconds. We continue.